In this video, I'll walk you through arc-based additive manufacturing simulation using the Goldog DFLUX Subroutine. In Abaqus, we'll simulate a moving heat source to model the wire arc additive manufacturing process step by step, including how to define the heat input, mesh the part, set the boundary conditions, and interpret thermal results with full thermal history. This tutorial follows a clean and reproducible structure, so whether you're building a thermal model for academic research or thesis work, you'll walk away with a working debug DFLUX setup. If you ever struggle with getting DFLUX to behave correctly or want to simulate wire arc additive manufacturing accurately without trial and error, this video is for you. Before we start, a quick thanks to the video's sponsor, HeatShape. HeatShape is a cloud-based simulation platform made for welding and additive manufacturing. No installations, no custom codings, just pick your process, define your weld path, and run the simulation right from your browser in a few clicks. If you're tired of debugging subroutines and want to run your simulations without headaches, this software is for you. I put the link in a pinned comment down below. Check them out on LinkedIn or their website to try this software for free. As always, we start with creating the part. So hit this one. Part 1 should be substrate because we want to create the layer separately. Should be 3D deformable solid extrusion, and this guy should be 0.2. Continue, and we need to create a simple rectangle just like this, and we select the dimensions 0.0025, and this guy should be 0.05, so enter, then scroll button, done, and this should be 0.05, and okay. Now we have the substrate. So what we can do here is to select the path of the DFLUX or where we want to put the layer on. So select on this one, partition face sketch, select this face, then done or scroll button, then this one. Now you need to select these two lines, scroll button, then this one, scroll button again. We need to know how much is this value, so it's 0.004, and okay, done. And we have these two lines. Now we want to extrude them toward this direction. For that purpose, left click and hold, then you need to sweep like this. You can select this line and hold shift select the other one. If you're using older versions of Abaqus like Abaqus 2017 or Abaqus 614, you cannot select both of them, so let's do it that way. Select this one and sweep along edge, then select this edge and create partition, then select this one, done, select this line, done again, sweep along edge, this edge, and create partition. But in Abaqus 2024, you can use them at the same time and extrude them, so it makes your life way easier. Anyways, let's create the layer. So we name this part 2 as layer. It should be the same, 3D deformable solid extrusion 0.2, and we need to create a rectangle again. So this should be roughly the same, but the thickness is different. It's 0.02. This one should be 0.05 again, but this one should be 0.04. So now we have the layer. This is the substrate and this is the layer. Okay, let's go to the property. To make your life easier, I uploaded the materials property in the feamaster.com website. So if you go to the shop, material property packs, and here you can select the temperature dependent properties of carbon steel, add it to cart, go here and do the checkout. You can download that for free. After you filled everything, you can download the temperature dependent properties. So let's open it. Here we have different things. Let's go to the Abaqus. The material is steel, and we need thermal conductivity, we need thermal specific heat, and we need general density. So all of them should be temperature dependent data. So from here we should find density. The first one is the density, so Control C to copy and literally paste it here, then go to the specific heat, use temperature dependent data and copy paste this value here, and for conductivity use temperature dependent data, and this is the conductivity. Place everything here and okay. Now it's time to create sections. So we need one section for solid, homogeneous, and the material is steel. Now we need to assign the section here, done, and okay. Now we need to do the same thing for the layer. So we just need to assign the section here, done, and okay, because we assume that both of them are having the same material. Okay, now it's time to go to the assembly. We need to assemble both of them and make sure that it's part dependent so that we can mesh each part dependently, and okay. Now we need to put this one from here. So we select this one to here. Now we have one substrate and we have one layer. Okay, now let's translate both of them to here. So select both of them and okay. Then we need to translate this part to here. So it's better to translate them once more. So we select them both and we select this one and select this one. The reason behind this is to define the 0, 0, 0 as the starting point of the flux, and it's easier to do that. You can do that without that, but you have to find this point as a starting point. So as we want to make things simple and starting with the 0, 0, 0, we translate this to here. Okay, we're done with assembly. Let's go to the step. Before performing any action, let's go and save the file. So I want to save this in a folder, like I can create a folder like Wire Arc AM and okay, and I can name this Wire Arc Additive Manufacturing, then okay. One more thing to do is to go from file and set the work directory to the specific folder. So in this case, every file we create, including IMP file, the jobs, and everything else would be stored in that directory. So to select that, we go here and we select the Wire Arc AM, and so we need to select Wire Arc AM and okay. Now as you see, it's C, temp, and Wire Arc AM. So if we click OK, from now on we can find the files easier. If you like this trick, please like the video to continue. Alright, let's create the step. Create a step. It comes after initial. It should be heat transfer. The time period can be 25. This one can be 1 million, so it is 6 zeros. Initial can be 0.1. This one can be 1e minus 10. This one can be 1, and this one should be 350 and okay. Then we go here to the field output manager, then we create this one. We don't need the RFL or we don't need the HFL, we only need nodal temperature. Then okay, dismiss, and we're done with this step. Let's go to the interaction. Okay, the first thing to do is to create a tie constraint. We want to tie this layer to the substrate, so we name it tie, continue. So select node region and we need to select this one, so Go from here, create a display group, put it on cell, edit, select this one, done, and remove. And we select this one, done. And now we need to select the node region again. So replace all, select this one again, cells, edit. You select this one, hold shift, this one, and done. Now we remove them, dismiss, and you can rotate the instance and press this one, select this one, and done. Let's put this one on this and replace everything. So we have the main surface and the secondary surface, and it's okay, done. Now as you see, the interaction is created. Now it's time to create the interaction properties. So we need to create the surface film condition, continue. First we select everything, then we rotate it using Control plus Alt and left click, or you can use this one. If you don't click anything on it, it shows you can hold Control Alt and mouse button 1, which is the left click. So by holding Control, you can deselect these parts, so we don't need the bottom part and we only need the surface, and done. Now we need to create surface film coefficient. It should be the property reference, and we need to create the material property. So from here, create interaction property. It should be film condition and continue. Use temperature dependent data and go back to the Excel file, surface film coefficient, Control C, come back here, Control V, and okay. This was the property of air. So if your model is in water or anything like that, you should use another interaction property. So this is selected. The sink temperature can be 25 and okay. Now we need to create another interaction. So from interaction here, we need surface radiation and continue. Then again, we select everything, control, hold Control and deselect this one, and done. Let's put it back here. The emissivity must be 0.49, and the ambient temperature is 25. And okay, as far as I'm concerned, we've done everything in the interaction. Now it's time to go to the load and boundary condition. This is by far the easiest part, so we need to create a load here in step 1. And it should be body heat flux because it's Wire Arc Additive Manufacturing and we want to use gold duct model. If you want to use a surface heat flux, you need to create a subroutine for Gaussian distribution. This is the body heat flux, continue, and we need to select this one, done, and we put the magnitude of 1 here. Instead of uniform, you select user defined. So it says you need a user-defined subroutine DFLUX, and okay, now it is created. Now one more thing to do here is to create the predefined field. So we need to select step initial, and from other, you need to select temperature, select everything, done, and it should be 25, which is the initial temperature, and done. Now we're done with the load. Let's go to the mesh. Meshing is very important, so attention please. By the way, if you enjoyed this video so far, please share your feedback with me in the comments down below. It's totally free for you, but it gives me the motivation to continue and creating more videos like this for you. Thank you. Now we go to the part. First we go to the substrate. Okay, now we want to see the edges. First we select this one, hold shift, select these 4, these 2, and these 2, done. Put it on by number and add a 0 here, so we need 40 elements on this direction, and okay. Now let's select others like this one, this one, this one, and this one, and done. This should be 6, and okay. Now you need to select every line parallel to this one, like this one here, here, and here. Okay, done. This should be 4 and done. Let's mesh it. This is the mesh. As you see here, we have a refining version in this direction in the middle. Now let's go to the layer and do literally the same thing. So this one, this one, this one, and this one. These should be 4. This one, this one, this one, and this one. They should be 6, and last but not least, these guys must be 40. And if you go, oops, now you need to mesh it, and if you go back to the assembly, you see that all of the lines are matching here and here, and if you rotate you can see the lines are matching here, and if you go the other side you see everything are in line. So it's very important to do such a thing. If not, there would be a mismatch and it reduces the accuracy of your model. Okay, one more thing to do is to go back to the part, assign element part, and this should be heat transfer. Then okay, now we go to the substrate and we should select everywhere, and this should be heat transfer again. Now we should go to the model, and from edit attributes, model 1, we should define the absolute zero temperature, minus 273.15, oops, 1 and 5, and we need to select Stephen Boltzmann. This should be 5.669 E minus 8, and okay. Now that we selected everything, let's set the global size at this one. So if I okay and mesh it again, let's go to another one, the substrate. Let's put this one on 20 and auto delete the mesh, and as you see the mesh is now in a better position. We go to the job. Now it's time for the subroutine. Okay, now I open the Visual Studio 2022. So we go continue without code, and from here file, new, and file. I want to create Intel Fortran and .4 file. I open it. Now this is the file I have. Now we need to go to the Abaqus documentation. Now here in Abaqus, if you go all the way down to the user subroutines, and we need the Abaqus standard user subroutines and DFLUX. This is the code for the DFLUX, so I always recommend you to copy and paste it from here. Don't trust any other sources. Then you go back here and paste it. As you see here, we have subroutine DFLUX, and here is where we need our code. So this is the code. We have the coordinates X, Y, Z, and we have the heat source center. We have X, Y, and Z here, but for XC we have X0 plus V, which is the welding speed, times T. So in this manner the flux would move. And here we have the Goldach parameters. So these parameters are for the ellipsoid A, C, PF, PR. If we take a look at this image of the Goldach double ellipsoid, you see here we have the front and the rear ellipsoid, and we have A, B, and C. So as our coordinates are not the same as this one, we have two B's. So here we have PF and BR, and we have A and C, and this is F for front and F rear, which is one coefficient, and the summation of these two coefficients should be 2. So if we take a look at this article and we go all the way down to these equations, we have this equation for the front and we have this one for the back. Actually, the front would passes through the temperature and the rear ellipsoid maintain it. Here we have for the x bigger than 0, and here we have this one for the x's less than 0. And this is the fraction FR over BR and FF over BF. And as you see here, the FF plus FR must be 2. They also provided the table including A, C, BF and everything else. I took FF and FR from them, but I wanted to have my modified version of the A, C and BR, in other words the ellipsoid, so I changed the numbers. You are allowed to change the numbers for your model as well. So let's go back to code here. We have the heat input parameters. The eta here is 0.8 VI, so basically we have the Q out of it. And here we have the QR and QF. Let's go back to the paper to see that. Here actually this is the part before the EXP term, and we have this one. So this is the equation for that, QR and QF. Here we have the rear half. This is the code for it. If the x is less than or equal to xc, you would have this one, and as a result the flux would be this one, QR times the exp. We basically put the equation of the QR here, and we have an end if here, and there's an else if here. If x is greater than xc, we will have this equation here for the flux, and the flux 2 is 0. You might wonder what this and would be. So if I cut it and paste it here, you see it turns into a comment and it cannot fit there. So we put it here and we place an and, or we can place 1, or we can place a star here in order to define that this is the next line in continue of the previous line. And that's pretty much everything. If you need the code, just visit the website. I put the link for you in the description. Alright, we save this one and we go back to the Abaqus. Now we jump back to Abaqus to create a job. So I would name it Wire Arc Additive Manufacturing and continue. And if we go to the General tab, here it says user subroutine file. As we set the work directory here, it would open the folder, and this is the goaldoc.4. And okay, we can have the parallelization here. Let's put it on something like 8. And okay, now from here I would like to submit the job. We ignore this one and submit and wait for it. And as you see, the job is completed. Let's go and take a look at the results. So if I put it back here, first you can see that manually. As you see here, the flux is moving, and because we tied the layer to the substrate, you see the gradient of the temperature on the substrate as well. If you don't tie them together, you only see the temperature gradient on the layer. Okay, now as you see, it's moving. You can also put it back somewhere around here, and from here you can specify the limit. Let's put it on, for instance, 2500. In this case, you can see that better with the animation, I mean. Yeah. You might need to modify the ellipsoid parameters yourself. So this video has the educational purposes and we're not validating it with any experimentals, but most of the users first they run the job and then adjust the parameters to match. Okay, now another thing we can do is to go from here, ODB field output data, continue, and we can put this on unique nodal and nodal temperature element nodes, and we can edit the selection. We can select some nodes, for instance one here, and we can go through the thickness like somewhere around here, 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 here. Maybe it's better to select these two and not this one. So if you want to plot them, you see here we have the temperature versus time plot for different nodes, which is pretty common. And if you want to save your data, here you can right click on this one and edit, select all of them, or select the first one, go all the way down, hold shift, select the last one and copy that. And if you go to an Excel file, you can literally paste it here and you can plot them yourself just like this. And as you see here, we have the plot of time versus temperature. You can modify everything yourself, I mean the axes or the legend. Let's jump back to Abaqus. If we go here, we can also make the animation better or make the view better. If you hit this one and put it on feature edges, you don't see the meshes or the nodes, and it's more beautiful. Yep. And another thing we can do is to cut. For instance, here we can cut it to see how far it went, and you can, if you want to see the values here, you can go from here, and from probe values you can put this either on elements or you can put this on nodes. And if you put it here, for instance, if you click, it collects them and you know the nodal temperature here without plotting. You can move and track like this. Yeah, as you see here, it differentiates them. So we have layer here 2700, and in the same position the substrate is 1000, and you see the gradient here. And that's it. If you enjoyed this video, please smash the like button and subscribe to the channel to see more videos like this. Don't forget to watch the video on the screen before it ends, and stay tuned.